All right, so today we talk about derivatives of inverse functions. Now, we talked about derivatives of inverse sine functions, as I mentioned, inverse cos, inverse tan. Those are inverse trig functions. Now we're going to look at derivatives of any inverse function to any polynomial function, let's say, or any function, not just the trig ones, okay? So here I have on the right, and I have on the right a graph, okay? Now this graph, I'm going to redraw this, is a parabola. Okay, it's just a parabola graph. So that's a y equals x squared, whatever, x minus something, x plus something, squared plus something. It's a transformed graph, but it's a parabola. It's a quadratic. Now, the inverse, as we learned the other day, the inverse, right, is a reflection. It's a reflection about the y equals x line. So it kind of looks like this, right? This would be sort of the inverse function. It would be a flipping over of that y equals, here's the y equals x line. Okay, and we also mentioned yesterday that inverse means reverse, right? What are we reversing? We're reversing x and y. Okay, so we know that about inverse functions. Now, some functions, let's say it's a function like, you don't have to write this down, but let's say it's a function like this. That's a really crazy function. And to find the actual expression of the inverse, to actually switch x and y, and then to solve for y is going to be crazy, like nearly impossible for some things, okay? So to find the equation of this, which is not even going to be a function, right? To find the equation of this thing is going to be really crazy. So what we want to do is we want to work with inverses without actually determining what the equations of the inverses are, because that's a lot of work. And we're going to try and bypass that. And there is a way that we can bypass that. And I want to show you, first of all, I want to set this up by showing you this. So I don't know if you have this written down. We're going to let g of x equal the inverse of f of x, okay? Now, you should know what this is. Let me just see if you can tell me what this is. If we compose these two functions, so it's a composite function, f of f to the negative 1 of x, what does this equal? Very good. It equals x. Because we've really undone this, right? And all we're left with is our x there. Okay, very good. So if that's the case, I'm going to rewrite the same thing with our g of x inputted in there. Okay? You good with there? Good with that so far? All right. Now, if I wanted to find the derivative of this function, and again, this side equals x, this side equals x. I have nothing to do with the inverse, so, other than I have an inverse function in here, okay? So watch what happens when I take the derivative here. So I'm going to take the derivative of this function. Well, it's a composite function, which means there's an outer function and an inner function. So I'm going to have to do chain rule here. So this is going to end up to be, if I take the derivative of both sides, d dx of everything here, I get f prime of g of x. That stays in there. But I'm have to multiply by g prime of x, which equals derivative of x is 1. All right, that might not seem too earth-shattering just yet, but look at the title of our lesson, Derivatives of Inverse Functions. And looky what I have here now. I have the derivative of an inverse function, okay? So I'm going to isolate that now. So let's move up over here. So g prime of x is actually equal to, super simple, 1 over f prime of g of x. That's it. Now, what does this do for us? Well, what this does for us is this. I need to take the derivative of my original function. Hey, that's fine. Usually the original function is given. F of x equals something. That's going to be given, okay? And in all these questions, you're going to have the original function given. So finding the derivative of the given function shouldn't be too bad. Now, what about this business in here, okay? G of x in here. So let's think about g of x, okay? So where do I want to start? F of x equals y, right? Okay, so if we're talking about x and y, okay, f to the negative 1 of x. What does that equal? Sorry? Yeah, it equals g of x, but does it equal x or y? Sorry? Y prime? No, not quite. No, this isn't a prime. This is inverse. So it's inverse. Okay, so inverse means what? Reverse. So the answer is just x here. Now this is for the original function. Original function. As we can see, this is where we started, right? X for the original function, y for the original function. So the inverse function of x is actually equal to x. Okay? I'm not sure if there's another way I can show that, but we have x, we have y. This is x, this is f of x. Okay? Okay, what if I have f of y? Well, f of y equals x. Okay, does that make sense? Now, f of y is still x. F inverse of x is f of y. So if you trace this back all the way up the row here, you get f to the negative 1 of x is x. That's another way I can show that. Okay, so what does this mean here? This is the x value, and this is really important, x value of original function. Okay, so if we're evaluating at x equals blah, 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 what's the derivative of the inverse? You use the x value of the original function, or the y value of inverse function. Okay, so if the point is on the original function, you use the x value. If the point that you're given that you want to find the tangent to, or the slope of, or the derivative of, then you use the y value. Now this will come in, this will make more sense as we move through this. Okay, let me explain now why this is. So again, second part of this, I'm going to grab this, I'm going to copy this, and I'm going to paste this down here a bit. Okay, now why is this something special? For two reasons, really. There are two reasons are we do not have to solve for g of x. We just need to use a point there. Okay, we don't have to solve for g of x. We just need to use the point or a value in there. And the value is going to be the x value of the original function of the point we're dealing with, or the y value of the inverse. So we do not have to solve for an equation here. Okay, that's important. But watch this. I'm going to draw some derivatives. Okay, this derivative right here, that's the slope of a tangent line at this point. The inverse to this point is this point on the inverse graph. And here's the slope of the tangent line for that one. All right? Okay, that might not mean much to you, but let me zoom in and let me draw you another set of derivatives. Watch this very carefully. What color can I use? I'll use blue. Look at this one. This is the derivative at this point right here. That's the slope of the tangent. Okay, good. You good with that? The corresponding point would be this point right about here. And what's the value of the derivative at that point? Well, if this is m equals 0, this is m equals infinity. My whole point is this. Here was this one, here was this one. The slopes of the tangent lines to corresponding points on functions and its inverse will be reciprocals of each other. Okay, so if we have m is 0, if m is 0, okay, the slope of the inverse is 1 over m equals 0. See? 1 over 0. So we got 0, 1 over 0. Here's 0, and here's 1 over 0. This one's going to be something like 5 over 4 for a slope. This one will be 4 over 5. Okay? So it's always going to be the reciprocal. So how do inverses and reciprocals, how do they relate? Well, through this equation, check this out. See, you have, this is the slope on the inverse function. that's the slope of the tangent of the inverse function, it equals 1 over the slope of the tangent of the original function. So that's kind of, if you look at it that way, it makes a lot of sense. We're talking about reciprocals here. Okay? Reciprocals. Any questions so far? Okay. You guys are good. I got some more plans here. We got lots to go here, so we can solidify this. All right. This little theorem here, I'll read it real quick. If f is differentiable at every point on interval I, and df of dx is never 0 on I, then f has an inverse, and f to the negative 1 is also differentiable at every point. So this right here, okay, this is equal to 0. So this inverse here, it's m equals infinity. So that's technically not allowed, but it proves my point, okay? Okay. Let's keep going. Okay, derivative practice questions, page 2. Yep, let's go here. All right. All right, so we're going to work on these questions here. Now, here's an example of, I have an original function, f of x. It's x cubed, okay? It's a cubic function. You know, it might look something like this, right? Like that. Okay, I don't know exactly what it looks like, but we're wanting to find the value of the derivative of this inverse of this function. So what's the value of the derivative of the inverse of this function at this point? Now this is the given point. It's on f of x already. Okay, so this is some point that's actually on, you know, this inverse. It's a point over here that's actually on the inverse already. So they've given you that point. So what we have to understand is that we want to use the x value of the original function. Well, we don't have the point on the original function. We have the point on f negative 1 of x. Let me explain a little bit more about that when we get closer. So what are the steps? Well, in order to find this out, the derivative of the inverse, we find the derivative of the original function. That's really easy. This is 3x squared plus 7. You with me? You good with that? Okay. So find f prime of x. That's step 1. You might want to write that down. Step 1, find f prime of x. It's always the first thing you do. Given the original function, find the expression of the derivative. Okay. Second thing you want to do is you want to determine the x value of the original function. So this is the value on the inverse. The value of the original function, the corresponding point would be 110, wouldn't it? Okay. So that's the corresponding point of the original function. So the x that we're getting at is here, it's 1. Right? It's 1. Now, what if you didn't know what this point was? Like, you don't know if this is on the original function or the inverse. You can quickly check this out pretty easily, and this is how you do it. You go back to your original function, and you plug in, if you want to check this, you plug in 10 for x, and this is not going to equal 1, is it, on the other side? Instead, we put in 1 here, 1 cubed plus 7 times 1 plus 2, that equals 10. So that means that this is the x on the original function because they fit properly. You see that? So if you didn't know, you could always just do a quick check. Say, I don't know if this point is on the original function or the inverse. I don't know. Well, you could do a quick check. So here we found that x equals 1 on the original function. So x equals 1. Okay. So this is the value I'm going to put. Now let's plug things into the formula. So here we go. F to the negative 1 of x. Okay. That derivative, and this is where Leibniz notation comes in a bit handy, I guess, because to put a prime in here as well, it's going to be a mess. So that equals what? 1 over the original f prime, so d over dx of f to the negative 1 of x. So that's our formula that we used, which means this, simple. It's very simple. d dx f to the negative 1 of 1 is going to be 1 over the derivative of f evaluated at 1. So from above there, 3x squared plus 7 is going to be 3 times 1 squared plus 7. So it's simply the reciprocal of the value of the derivative at x equals 1 on the original function. It's the reciprocal. So this equals 1 over 10. Okay, so the slope of the tangent line, or the value of the derivative on the inverse function on this point, 10, 1, is 110. Okay, 1 over 10. Okay, so these steps, hope you have these steps. They're very simple. They're very simple, but what you do want to remember is this I have over in red. Use x from the original function only. Okay, so let's work on the second one. All right, so your function here is x to the 5th plus 3x cubed plus 7x plus 2. Okay, and we're looking at the point 13,1 on the inverse function. So I've graphed this original function here, and you can see that right around here, let's see if I can get to it again. Okay, here we go. We have on the original function 113. So we're given 13,1. So what I'm going to do is I'm going to show you this inverse. Let's duplicate this. We'll change that color to something different. And then I'm going to go y equals, here we go, 1 divided by 1. Okay, this is, let me just figure this out. Okay, so I'll just switch the x's and the y's. Yeah, that'll work. Okay, so again, 113 was, 113, right about there. So we got about 13,1 is right here. Okay, so it's going to be a pretty small value for a tangent line. It's going to be pretty flat there, it looks like. Okay, so let's go back to here. All right, so the derivative f prime of x is 4x, 5x to the 4 plus 9x squared plus 7, okay? And the value we're going to use is is it the 1 or the 13? Well, it's the x value on the original function or the y value on the inverse function, so we're going to use 1. So f to the negative 1 of x, the derivative is equal to 1 over 5, and I'm going to use the 1 to the 4th, plus 9 times 1 squared, plus 7. That is 1 over 5 plus 9 is 14, plus 7 is 21. So remember I said it's a pretty flat, the slope is pretty close to 0, should be, according to our diagram, and that is correct here. Okay, so just out of curiosity, let's do this. Let's do y equals 1 divided by 21. No, come on. X. Okay, so 1 divided by 21x. So this is, and what I'm gonna do is I'm gonna plus like W or something. Put a slider for W. So let's back off a little bit. So here's my line. You see this line? That is a slope of 1 over 21. Now if I move this up or down, I'm going to be able to probably slide this right onto, if I can. Oh, it doesn't look like it's quite touching yet, but you see, I'm going to see if, whoops. I'm going to see if I can get this so that it, oh, that's pretty close. Look at our intersection. Well, little tough to see, but this looks like it's a pretty good tangent line to somewhere around 13. So I could fiddle with this a little bit, but do you see how that slope seems to work? It's pretty close to a tangent. And I think that I might need to go like 0.45 or something. Anyways, it's going to be right around here somewhere. That's going to be 13.1. Right? And so that line right here, it works for a tangent, okay? It's not exactly on there. See, it's not quite touching, but I have to, maybe I'll go the other way. 3, 5, 7. Yeah, pretty close, right? So I'm just looking for the, that line right there. Tough to tell, but right now it's too low because it's crossing 2 points. Okay, I won't fiddle with this much more. 3, 8. Getting close. Oh boy, it's addicting. 3, 9. Okay, pretty close to 1 point. It's not showing up there anymore, but anyways, somewhere in between 3 and 3, 9. All right. You get that? 1 over 21. Sorry? Yeah, that was just trying to show you that a line with this slope can be moved up or down to kind of touch that graph, and it looks like it is a tangent. So if the slope was, if we were off, if this number was wrong, right? If this number was wrong, and I had something like 1 over 25, that's a bad one. 1 over 28. You see how it's like, that does not look like a tangent line. You can't really get close to that. That doesn't look like a tangent line for 13. It looks like a tangent line for maybe somewhere around 17. You see, it doesn't look like a tangent line for 13. And again, my apologies, this graph is really tough because everything is so flat here. It's tough to tell, but you'll be able to tell a bit easier with some other examples. Okay, let's do one more. Let's do one more together anyways. I'm going to erase this stuff because we're going to get some practice with the E. Sorry, I can't hear you.
Why did you put it like that?
Put it like what?
Like the points y than x.
The points?
Because x is equal to 0 and it's like the second point.
Yes, this is x in the original function.
The original function.
The original function f of x. This is the y on the inverse function.
Oh, okay.
Yeah, so this is the point on the inverse function. Right? Point on inverse function. So we use the y value of that point on the inverse function, which is the x value of the original function. So you always want to use the x value of the original function. Okay, so I do have some answers here. Let's take a look at the answers for the first few here. 110 we got. All right, so the answers for the rest of the problems here, find the derivative of the inverse here. For number 4, the fourth one should be 1 over 9. Number 5, this one's a little bit more complicated. You got to do the product rule here, right, to find the derivative, the product rule. But the thing is, you don't have to simplify, really. You don't have to simplify. All you do is plug in your number in for x. So you can use the unsimplified version. And you should get an answer of 3 over 11e. Anybody get that?
I got 3 over 10e.
3 over 10e? I think it should be 3 over 11e.
Because if you multiply 2 by 5, that's 10, right? Oh, it's plus.
Yeah. Anyways, we can come back to that one. But let's do the 6th one. Okay, so the 6th one here, again, they're getting a little bit more involved. Oh, and I said I was going to pause a little bit on this one. So how do you find the derivative of this? Well, it's quotient rule. Remember? Derivative of the top times the bottom. Derivative of the top here times the bottom minus the top times the derivative of the bottom all over the bottom squared. Now, they multiplied this. Look at, in this solution manual, they simplified this a bit. You do not have to simplify this. You do not. You don't have to. All you have to do is plug in the value that you have there for x. So wherever you see x, plug your value in, right here and here and here and here, and then just get a value, okay, equals some value. And so then you just do 1 over that number. It should be 1 over 3. Okay? So the derivative evaluated at, and what's this one? This one was what? The 6th one? This one right here. So evaluated at -1, 0. The x value of the original function is this 0. And so you put in 0 in here, in wherever you see x. That's all you need to do. You don't need to simplify. This one here is pretty complicated, okay? So they did a lot of simplification here, and then they substitute at the end. You really don't need to do that. Yeah, you really don't need to do that. Once you get the derivative here. Okay, so let's just pause and just do this real quick. So what do we get here? We get, on the top, I get 0 plus 1, so I get 1, times 3 times e to the 0 is just what? That's 3, minus negative e to the 0, so that's negative 1. So minus a negative, okay, so minus, this is negative 1 times 0. Is that right? All over 0, 1 squared, over 1. So this is 3 over 1, or 3, right? So that's the value of the derivative at 0. So you can bypass all this, and you can just go 1 over, what is this? 3. Boom, done. So you do not have to do all of this stuff here. You really don't in this, okay? So I'm not telling you have to do that. There's a bit of a shortcut. All right, so the derivative, this is 1 over f prime, evaluated at, or 0. 1 over 3. Okay, so you don't have to do all the fancy simplification in the middle there. All right, question, yep. All right, so what I want to do is I want to show you 2 AP exam questions that are copied from a practice exam. All right, so this is exactly what you're going to see, something just like this on your AP exam. And you're going to know how to do this pretty easily. Because you're going to read this and you're going to say, okay, let f of x be this. Okay, this is f of x. Let g be the inverse, okay, of f. Given that f of 0 equals 1, what is the value of, okay, so you read this and you're like, okay, derivative of inverse. Derivative of inverse. G prime of 1, that's the derivative of the inverse evaluated at 1, is 1 over f prime evaluated at, oh, what is this? What is this number? Okay, so this is where you start. And you go, g of 1, boy, is that the x value on the inverse function? Yeah, if it's written like this, it is. It's the x value on the inverse. So this is actually y on the original. And over here, you see, hey, f, this is the original function. Here's my y value. What is the x value associated with that? 0. So this is the x of the original, right? X original. So guess what? This is 0 in there. You with me so far? Okay. I'll finish it up here now. So then you go, oh, no problem. What's the derivative of this? So I need to find f prime of 0. Well, that's going to be 3 times 2, and x is 0. So I'll do all this at once. Squared times, derivative of the inside is 2. I see. So this is 0 plus 1, so it's 1 squared times 3 times 2. So 3 times 2 is 6. So I need to do 1 over 6. And that's my g prime of 1. And you look around and scan here, there you go. It's D. All right? Any part of that you want me to do over again? Because it did go pretty fast on that one.
I just don't like, because they didn't give you any points, you put f of 0.
Okay, so they didn't give you any points. This is them giving you a point. So this is what you have to understand about the AP exam. They are not going to give anything to you plain. You're going to have to use your head for a lot of little things in the question too, which is fine. X, the point x, y in this is, here's x in here, right? That's x. And this is the y. So yeah, you're going to have to kind of like, there's going to be multiple layers of these questions. Okay? And so you say they don't give you a point. Well, in showing you this, you can get x and y out of that. Yeah.
That's like f of 0 equals 1 is equal x equals y.
That's f of x equals y. Exactly. So our x is 0 and our y is 1. Exactly. And that's on the original function f, right? So this is why you use the 0, because it's the x value on the original. Okay, awesome. I tell you what, why don't you guys try this one? Here's another question from the AP exam. Go ahead and try this one on your own and see if you can get it done. So this question has one little wrinkle. And where do you see the wrinkle? What's different? Do you see it? The G. Okay, the G. This is what they give you as far as original points. Okay? Now this is the x value of the inverse. You see? Inverse is G. This is the x value of the inverse. So do we want to use the x value of the inverse? No, we want to use the x value of the original function. So do I use 2 or 0 in my calculations? I use the 0. I use the 0. That's right. That's the one wrinkle. So that's what they're going to do. They're going to do stuff like that on the AP exam. They're gonna think, oh, they're just gonna grab the 2 because that's what they've used to been doing, and they're not really thinking too much. Okay. This is g of 2. Okay. So what's the derivative? 3x squared plus 4. Okay. What's the derivative evaluated at 0? 4. So g prime of 2 is where I have 1 over f prime evaluated at 0. 1/4. Boom. 1/4.
I got the answer
Okay,
right away.
good.